Hello guys, today I'm going over the Java collection vector class and also its child class, stack. First up, vector. So the early days of Java, 1996, birth of Java 1.0 as well as the vector class. And you'll see that of course these legacy classes, they have characteristics of languages at that time. So why am I talking about vector at all? You're probably wondering. Are these legacy classes even used anymore? Do I need to know this? It sounds a lot like ArrayList, so why is this thing still around? Well, it's true, you're probably very rarely going to find it used in a project. It's really just around for backwards compatibility. It's always good to know history though, because it's helpful for understanding the present, right? So even though in programming you'll probably only use ArrayList and not vector, it's helpful for understanding any new features in a language or technology if you understand where it's coming from and how it's an improvement on the past. So if you're really into programming in Java like me, it's helpful, it's useful, it's interesting, and totally worth your time. So here we go. Vector 1.0, the last of the three child classes of List we're going to talk about. Vector was refactored in 1.2 to be compatible with List, and it implements random access as well as serializable and clonable, and its underlying data structure is dynamic array or resizable array. So there are a few things it has in common with ArrayList already. The big difference is that it's synchronized, which should equal thread safety, but actually it's a little weird with vector. It's synchronized but not entirely thread safe. I won't go into all of that right now, but it's definitely one of the big drawbacks to vector, as it's still slower than ArrayList or linked list. Don't forget ArrayList, linked list, both are non-synchronized by default. We've already looked at how to get synchronized versions of ArrayList and linked lists with the synchronized list method in the collections class, and later on in future videos we'll see that you can also get synchronized versions of set and map objects. So how about the constructors available to vector? So ArrayList we had 3, linked list there were 2 constructors. Vector, I guess it stands to reason that vector would have 1 constructor, right? I mean 3, 2, 1, that's logical, right? Well, that wouldn't be a safe bet because vector is coming in with 4 big ones. We've got our default constructor. It has a capacity of 10. We have another one that takes the initial capacity. Third one takes initial capacity and the incremental capacity. We'll talk about that in a second. And of course the constructor that takes a collection. So let's take a look at the first one. It creates an empty vector object with a capacity of 10. And unlike ArrayList, you remember ArrayList, it would resize by taking the current capacity, multiplying times 3 divided by 2 plus 1. This is how ArrayList resizes. Vector, not so efficient, it just doubles. So current capacity equals current capacity times 2. The second one, this creates an empty vector object with the specified initial capacity. So it's better to try and set the capacity at creation time if you have some idea, rather than doubling your list 100 times. And the third constructor, now here's something ArrayList cannot do, some flexibility with resizing that ArrayList doesn't have. And this helps make up for some of the more potential wasted memory due to the way vector resizes. So this one, we have an initial capacity and the incremental capacity. So if we have a vector, let's say 1,000 cells, and we just need room for a few more, it would be such a waste to double our list again, to have 2,000 cells, and we only need 5. So this is how we can take care of that. And by now you are no stranger to this constructor, which converts one collection object to another. So those are the constructors available to the vector class. So names, traditionally, historically, you would find that names, they were lengthier in the old days. And we can look to popular music to illustrate my point. So Mozart's name, this was actually Mozart's name when he was born, Johannes Chrysostomus Wolfgang Theophilus Mozart. So after Mozart, names continue to shorten. We have some artists who just either they use some initials, other bands. They never even went beyond the first 4 letters of the alphabet. Of course, the ultimate example was Prince Rogers Nelson, who shortened his name to Prince for a while, and then eventually changed his name to what looked like a fish hook. So my point here, if I have a point, is that as history moves forward, names seem to keep getting shorter and shorter. And Vector is somewhere between Mozart and Run DMC. You know, some of the method names can be a little long. Let's take a look at some of those now. So up top here, you can see a few of the methods that apply to ArrayList and LinkedList. Now compare those to some of these legacy methods that we have in Vector. We've got add element. Instead of add, we have add element, insert element, add, set element, add, remove element, add. I don't know if you're seeing a trend here, but I think prepositions were all the rage back in 1996. And you can see that the names are relatively long. Now something else that you may have noticed, for example, in this insert element at method, it's taking the object, in the parameters, it's taking the object first and the index second. So that's a little unusual. You probably noticed that. Let's go ahead and run this code and see what we have. So there is our vector, the first 2 objects we added, and then we inserted Todd at the 0 index. So that is not optional. You can't switch them around the other way. Let me show you that really quick. So if we put the index first and then we try to insert Stewart, compiler is going to try and give us a smack. You're looking right there, wrong, second argument type. So the order of the arguments is very important. Whenever you have a free moment, taking a coffee break, it's always good to take a little stroll through the documentation here. You can look at Vector, you can check out some of the other methods that are available. There is our add. See, so as of 1.2, Vector is inheriting from the list interface. So it has these methods, add, clear, etc., etc. And so there is our add element method, which adds the specified component to the end of this vector, increases its size by 1. So as far as I know, this is identical to this add method in every way, except it has a longer name. So if you like typing, if you like long names, you could go for the add element method. But here we have a slightly better and newer version of that method. It has the same functionality. What else do we have here? We've got contains a copy into. There's an ensure capacity. I'm going to get back around to that method another time, I think. We got hash code. Oh, here we go. Splitterator. Sounds like a superhero. So up until now, when we were talking capacity in regards to ArrayList, it's going on under the hood. We don't see our capacity. And with collection, we generally don't have to worry about it. But in Vector, we saw that we can affect the capacity via our constructor. So our program can actually increase the capacity of a vector before inserting a large number of components. We can also see what the capacity is with the help of the capacity method. Let's take a look at that. Here I have a new vector object. I named it vec. And I'm using the printf method to show its default capacity. Then we're populating old vec with integers 1 through 10 and printing out the results, and then showing the capacity, which should be unchanged. Here's a string with the reference 1 too many, and we're going to add that to vec. Since I'm not using generics, I can do that. We print out the new vec, and then show what our capacity has increased to. Let's go ahead and run that. So there you go, there is our initial capacity, original list of numbers 1 through 10, showing the capacity is still the same after adding them. We add resize me, and here is our increased capacity. Original capacity times 2 as expected. So pretty much the same program, except this time let's give vec our initial capacity of 25, and let's go down here. Change this and we'll count all the way up to 25. Let's run that and see what happens. So there is our initial capacity of 25. We're going to count up to 25, still 25. Then we're going to add resize me and we're going to double up to 50. Now what if I give it an increment capacity of, let's say, 5, and then let's see what happens. So there we go. We add resize me, and we only need to increase our capacity by 5. We now have a capacity of 30. Okay, a quick refresher on stack. In computer science, stack is an abstract data type. We have two principal operations, push and pop, and we can push an element onto the stack and pop it off the top. So it's a last in, first out design. So we can push Larry here onto our empty stack and we can pop him off, or we can push Shemp onto the stack and then we have to pop him off before we can get to Larry. Now stacks can be implemented to have a bounded capacity. So if the stack is full, like this one, and we try to push another element onto the stack, we are going to go into stack overflow and crash.
Good night.
So here's the stack class, came in Java 1.0. It's a child class of vector designed for last in, first out types. It implements serializable, clonable, and random access, as well as collection list and iterable, of course. And here is our constructor. It creates an empty stack. Not too much else to say about stack. If we go into the documentation here, we can see that Oracle recommends that a more complete and consistent set of last in, first out stack operations is provided by the deck interface and its implementations, which should be used in preference to this class, for example. And it gives us an example here of deck and its implementation class, array deck. Of course, we're not going to listen to them today. Let's go check out the stack methods. So here's our push method. It inserts the element onto the top of the stack. Here's pop. It removes and returns it. Peek is just going to give us a look. Empty, it's the same as is empty. It's going to return true if our data structure truly is empty. And look here, the search method returns the offset. So offset, what the hell is that, you ask? Well, looky here, on this side we have the index. Remember, stack implements random access. So we have an index here starting at 0, of course, and we count from 0 from the bottom of the stack on up. Over here is the offset, which starts at 1, and we count down from the top of the stack. So 1, 2, and so on. Shemp here is at index 1. He's got an offset of 1. Larry, index 0, offset of 2. So let's head over to IntelliJ and check these methods really quick. So here we are. I've imported the stack class, and I've created a new empty stack. We're going to push on the items Mo, Larry, and Curly. So first Mo is going to be on the bottom, Larry will be on top of Mo, Curly on top of Larry. And let's go ahead and we print that out, and I'm looking at Mo, Larry, and Curly just as expected. Print out, sorry, here we go. We're going to check and peek at the top of the stack. So Curly is at the bottom of our code here, but he is at the top of the stack. We're going to peek and make sure he's there, and he is there. And then we're going to print out again and make sure he's still there. So Curly is still on the list, as you can see. Now here, we're going to pop this time, and Curly should be removed from the stack. So it's returning Curly, and you can see Mo and Larry, but no Curly. Now we can check to see if our stack is empty right here. And you can see false, it is not empty because we have 2 elements on our list. Now we're going to push Shemp onto the top, and then I'm going to search Curly because I want to see what is returned if for an offset if the item is not there. And then lastly, we'll check to see if Shemp's there and what his offset is. So Curly is giving us -1. So this is what happens if the item we're looking for isn't there. We use the search method. It's going to return the offset of -1. Of course, Shemp is there, and it's giving us a 1 because Shemp is going to be at the top of the stack now. So our stack is basically going to look like this. We're going to have Shemp, Larry, and Mo. Index 0, index 1, index 2, offset 1, offset 2, offset 3. Guys, thank you so much for coming back this time. I hope you learned something. I hope this was informative, helpful, entertaining in some way, on some level. Coming up next, the 3 curses of Java. I will see you then. Take care.